Hi, I'm Junso Ha, and I'm here to present our Group 15's project for CS4641. The project title is New York City's Taxi and Limousine Commission Trip and its record data analysis. This presentation will include introduction as well as the problem definition, the methods, and finally the results and discussions. In the heart of New York City, the iconic yellow taxis not only drive the city's relentless pace, but also tell its stories, its journey a unique narrative contributing to an extensive dataset. This project explores this taxi-centric dynamics through supervised and unsupervised learning, seeking to understand and illustrate the city's complex, never-ending rhythm. Despite the apparent importance of taxi services in New York City, there remains limited comprehensive analysis on how these services interact with the broader city dynamics. The key questions that we came up with include: where are the highest demands for taxis and at what times? Are there underserved regions in the city that need better taxi accessibility? How do ride durations and distance change based on various factors, and can these factors be predicted? By diving deep into the New York Taxi TLC trip record data, we aim to answer these questions, offering actionable insights to stakeholders ranging from city planners to taxi operators. This study will not only enhance our understanding of New York City's taxi ecosystem, but will also present strategies to elevate the experience for both drivers and passengers. For data collection, we selected the July data for Yellow Cab and convert the Pocket file to CSV file for convenience. The trip records of yellow and green taxis contain detailed information such as the dates and times of pickup and drop-off, locations, distance traveled, breakdown of fares, types of rates and payments, and the number of passengers as reported by the driver. These datasets were gathered and supplied to the New York City Taxi and Limousine Commission by tech providers approved through the taxicab and library passenger enhancement programs. We chose the linear regression as our initial approach for predicting taxi fares due to the inherent linear relationship between distance traveled and fare amount. In the context of taxi services, the fare typically increases in a proportional manner relative to the distance covered. This relationship is ideally suited for linear regression, a model that excels in situations where the dependent variables changes linearly with the independent variable and distance. By applying linear regression, we can effectively model and predict fares based on distance, taking advantages of its straightforward computation and ease of interpretation. We decided to use random forest learning for our unsupervised learning model because taxi fares often depend on non-linear relationships between variables such as distance, time of the day, traffic conditions, and special zone fares, and random forest can capture these non-linearities effectively. Also, it can naturally model interactions between different variables without the need for explicit feature engineering. For example, the interaction between distance and time of the day can significantly affect fare amounts. Lastly, random forests are less prone to overfitting compared to some other models, especially if there's a large amount of data available. This means the model can generalize better to unseen data, such as predicting fares for new routes or under different conditions. The initial data comprised 200,000 rows of taxi trip records, which were filtered to remove any trips with negative fare amounts. Following this cleanup, we observed that most trips in the dataset are short, with a small peak at approximately 13 miles, potentially indicating common airport routes. We also identified and excluded any trips with missing data to maintain the integrity of our analysis. We also established a bounding box around New York City using the min and max coordinates from the test set and visualized pickup and drop-off locations on a map of the city. This visualization highlighted areas with high taxi activities, particularly around central Manhattan, and allowed us to focus our model training on the most relevant geographic data. Histograms of fare amounts near key locations such as JFK, New York, and LaGuardia airports showed expected peaks corresponding to typical airport fare rates. We also noted that the fare amount tends to increase linearly with distance averaging around $5 per mile. The data suggests a significant number of trips occur within a 1.5-mile radius of JFK Airport, with the concentration of fares between $50 and $60, which corresponds with the fixed rate fare to and from JFK. Trips with zero distance but non-zero fares presented a challenge as they likely involve minimum charge trips or other fixed rate fares that is irrelevant to distance traveled. Off-peak hours and nighttime rides incurred different fares compared to daytime. Trips distances greater than 15 miles from the city center showed a wider variation in fares, which shows locations significantly impacts fare pricing. Our random forest regressor for non-supervised learning was trained with an extensive range of hyperparameters. The evaluation of the test data yielded an RMSE of 8.62 and an accuracy rate of 75.45%, within an acceptable error margin of $5. This is just a reasonable level of predictive performance, albeit with some room for improvement. The linear regression model showed superior performance in terms of RMSE and R-squared, indicating better predictive accuracy and the ability to explain a higher proportion of the variance in the fares. The random forest regressor, while slightly less accurate in terms of RMSE, provided robust predictions with a significant portion of them failing within an acceptable error range. The analysis of the New York City taxi trip data, encompassing data pre-processing, geospatial analysis, and fare analysis, provided critical insights into the dynamics of taxi services in the city. The identification of short-distance trips as prevalent with a noticeable concentration around airports, particularly JFK, shapes our understanding of the taxi usage patterns. These findings are corroborated by the fare analysis, which showed a linear increase in fares with distance, highlighting the conventional fare structure in the city. The analysis of New York City taxi data revealed essential trends like the prevalence of short-distance trips and a linear fare increase with distance. The linear regression model's high accuracy highlights a primarily linear fare structure, while the random forest regressor captures complex nonlinear patterns despite being slightly less precise. The data suggests that New York City taxi fares are based on a mix of linear and non-linear factors influenced by time and trip origin. For future improvements, further refinement of the models seems necessary, especially in integrating other factors like traffic conditions, weather, special events, and time-based fare variations. Considering the strengths and weaknesses of both the linear regression and random forest regressor models, hybrid approach combining linear and nonlinear models could potentially yield better predictive performance. Future models could benefit from revolved time data integration, providing more dynamic and accurate fare predictions. Also, analyzing a more extensive data set over different time frames could reveal additional insights, particularly regarding seasonal variations and long-term trends in taxi usage. Thank you.